Okay guys, let's get started. This is the slide that we left off with. We talked about the angular velocity of an aircraft in flight mechanics involving three different quantities P, Q and R, which are essentially having the units of radians per second. But we also introduced the corresponding angles phi, theta and xi. But we just warned that P is not phi dot, Q is not theta dot, and R is not xi dot, but they are indeed related with each other, and that we can decipher once we go to understanding that mixed basis in which those rotations happened. The first rotation happened about B3, the second happened about B2 prime, and the last one happened about B1 double prime. Okay, so rather than about B1, B2 and B3, which is what we want to factor in order to understand the relation between phi theta xi on the one hand and PQR on the other hand, which is very critical because there's a certain thing which is actually read by the rate sensors on an IMU and what is actually wanted, and therefore in terms of the change in orientation, and unless and until we have a relation between PQR and phi theta xi, we will not be able to do that, which is the purpose of this set of exercise. Also the fact that you'll understand the complicated nature of finite rotation as opposed to infinitesimal rotation. So angular velocity in terms of orientation angles is what we want to get into, for which we will utilize something that we did towards the end of last lecture, and we very quickly revised at in the morning, where we said that when we want two quantities related in terms of their angular velocities, and we see that the complicated rotational motion is involved over there, then we can actually break it up into smaller parts, each of which could be a reasonably simpler, relatively speaking simpler. But in this case, it even becomes a simple rotation because it's about one particular axis. So what are we trying to do? In getting from earth fixed A to the aircraft fixed or body fixed B, we are moving in steps from A to B prime first, then from B prime to B double prime, and finally from B double prime to B. Okay, so each of these we now know how we got into. Let's again go from the right end, more like an Arabic or Urdu script, where we are looking at from the right end because that's how we started. Remember, it's a 3-2-1 system rather than a 1-2-3 system. So what did we do? First time we rotated it by an angle xi about the A3 axis, which is also of course B3 prime, but it's the A3 axis, which is what you see as the last term here in the second line here. So it's xi dot times A3 hat, right? So that's the first thing we did. So now we no longer had the B1, B2, B3 system to play with, but the primed system is what we had to play with. And when we did that, we had a rotation about the B2 prime, and that is by an angle theta. So obviously when you're talking of its rate, then you're looking at theta dot. Okay, so when we are saying that omega and the dots cannot be related, they cannot be related directly in a B1, B2, B3 system or an A1, A2, A3 system, but it's a mixed basis because the rotations are taking place about different sets of bases. Okay, so next last rotation that we had was you see about the x1 axis, and that is essentially what you see over here, which is the x1 now became your B1 double prime. Okay, so which is what you see over here, B1 double prime. Along that there's a rotation by phi, and therefore the rate of rotation is phi dot. Okay, so now it's very clear what we have, but we also know that because during all of those rotations were simple about a particular axis, therefore A3 is equal to B3 prime. Similarly, your B2 prime and B2 double prime are equal to each other, B1 double prime and B1 prime are equal to each other, which is what are the equations we wrote over here about the rotations that are taking place. We are just restating that. We are using these equations to replace that. So the first term, for example, I'm replacing in the second line there is a B1 double prime, I'm just replacing it with a B1, right? So same thing we are doing for the others as well from these equations. Okay, so now two alternate ways of putting this, if you want it in the simplest form where there are just three terms and each term is a product of two quantities. One is a measure number, the other is a unit vector. But both these methods are involving mixed basis. Neither of them is talking about a single particular frame's unit vectors, but three separate frames. From each frame you're choosing one particular unit vector, and of course you can mix and match and you can get, but at the most you're probably going to get, for example, if I use this term and this term, I might get both of them in the double primed system, right? So similarly, if I use so I think that's the one case. Yeah, if I use these two, then I can get at least two of the components in the prime system, but still one of them has to be either in the unprimed or double prime system. So that's the issue that we have, that we can't put all three of them in the same system. And therefore these quantities, remember we introduced PQR as the roll rate, pitch rate and yaw rate, but phi dot, theta dot and xi dot are not the roll rate, pitch rate and yaw rate, because they are about different axes. They are not about the body fixed axis. They are not about B1, B2, B3. If they are about B1, B2, B3, then they are the roll rate, pitch rate and yaw rate, which is why we when we say the same omega that we were dealing with, that is omega of B slash A, we were writing it as P along B1, Q along B2 and R along B3, and all of them hatted, and then it was in the same system. Then you could call it roll rate, pitch rate and yaw rate, but not in this particular mixed basis or any mixed basis for that matter. Okay, and also in a few slides going forward, since we have only two bodies, we may not explicitly state that it is B slash A. We might just write it as omega and understand that it is omega of B, that is the body, with respect to A, the earth fixed frame of reference. So then this is just by using unit vectors, but of course we have introduced the concept of the direction cosine matrix as well. We can utilize that in order to express the intermediate frames, because the only issue that we have is that they are in different systems, but we can bring it all to a common system, and in particular to the B system that we are interested in, because that's how the pilot gets the feel for what is actually happening. It's in the aircraft fixed frame because he is fixed to the aircraft. So essentially you're looking at the direction cosine matrix as a tool in order to express all the intermediate frames of reference unit vectors in terms of the big B system without the primes, which is essentially a rigid body fixed frame of reference and its unit vectors B1 hat, B2 hat and B3 hat. Then you can directly correlate with PQR. We can see the term to term match of the measure numbers. Then we can see how PQ and R are given in terms of not only phi dot, theta dot and xi dot, but also sines and cosines of these angles. The angular velocity vector, omega, the measure numbers represent any frame of reference, implies you have to find the measure numbers in the rigid body frame of reference, which we know is PQR, but we want it in terms of the phi, theta and xi dots. So this is what we had as a definition for PQ and R if omega is expressed purely in the big B system, which is involving the small b unit vectors. So when we actually do that, which means that those three direction cosine matrices that we talked about in the morning, we just need to have invoke them in an appropriate way, and each case you have either only a xi or only a theta or only a phi, those three rotations in 3, 2, 1 sequence. Once you invoke that, you see that your final result turns out to be this. So in other words, the previous slide gave you omega in a mixed basis system. Those unit vectors which are not B's, namely B1 primes or B2 B double primes or the A, etc., those had to be expressed in B using direction cosine matrices. Once you do that, this is what you would get. Now, a very simple way to kind of verify this is to take to the degenerate case where both all these angles that are involved, phi, theta, are all equal. In fact, you can see that xi is not involved. That's a very interesting thing, that xi is not involved in terms of sines and cosines. Of course, xi dot is there, no doubt, but you see that the sines and cosines are all about of just the pitch and the roll angle. Can anybody say why this is so?
does it have something to do with the fact that we use the yaw angle first? Or?
Exactly. And because we did it first, it is about your B3. So it's already about B3. So it's not in one of the primes or double primes. So even though, of course, B3 prime is equal to B3, but it is already in the form of B3. So which is why there is no transformation from a sine cosine point of view for that. On the other hand, it adds terms to all three. To P, Q and R, there's a contribution by xi from all of them. Yeah. Whereas it's not so about phi or theta, because for example in this there is no theta, there's no pitch contribution to your roll rate. Yeah. So that is one thing. The other thing is, if you can look at the degenerate case where phi and theta are equal to 0, that is, there is no roll or pitch, then you see all the sine terms will go away, the first two terms here and this term, and the cosine terms will just become unity, which means that this will just be phi dot, theta dot and xi dot, which is what you intuitively think. So but that intuition is valid only when your phi and theta are equal to 0, otherwise that is not valid. Okay, so just keep that in mind. But this is a general set of equations, always valid for irrespective of what the values of phi, theta and xi are, however large or small they might be. This is a valid set of relationship, and these are extremely useful in aircraft dynamics. In fact, they become some of the very basic equations. A lot of aircraft dynamicists even memorize this because they use it so often. The angular velocity vector, now the same equation what we wrote in the previous slide, it can be remembered in a much more easier way if you write that in a matrix form. When you write that in a matrix form, you get the relationship between PQR as a column matrix on one hand, with phi dot, theta dot, xi dot on the right hand side. And this column matrix involves, of course, the sines and cosines of theta and phi only, not of xi, which, as we just described, is the first rotation, and therefore happening about, as you see over here, B3, and therefore there is no need for sines and cosines of that coming into the picture over there. Okay. The other thing to remember is this is neither the direction cosine matrix in general, and this particular direction cosine matrix need not be symmetric, need not be anti-symmetric either. Okay, so it's a fairly complicated matrix in that sense. But yes, there are a few zeros, so there is a level of sparsity that you can take advantage of, especially in your numerical implementations, etc. But for that, essentially, it involves some non-linearities as well, because already, except for these four terms, every other term is involving at least one level of non-linearity, because there's remember that phi, theta and xi are unknown quantities. So you are having a sine of theta, already it's a non-linearity. Then it is multiplying essentially xi dot, because the last column. So you see that there is a non-linearity, and there are up to the level of third level of non-linearity. But of course, remember, these are cosines, and if you actually expand them in power series, you get an infinite series in a power series of theta and phi. So these are very high levels of non-linearity that are involved, and typically you have fairly large angles, so you can't drop off the higher power terms either, so they remain. And so it's a highly non-linear equation between the roll, pitch and yaw rates with the roll, pitch and yaw angle rates. So these two are related by fairly highly nonlinear relationships. And still, remember, it's only the motion description stage at which we are, which means it's a kinematic equation. It's an equation which relates angles to their rates, right? So this is purely a kinematic relationship. So you have nonlinear kinematics for this particular problem, and sometimes from the kinetics also you can get a level of nonlinearity, but usually the level of nonlinearities that you get from the kinetics is not as high level of nonlinearity as you get from the kinematics. And of course, the same thing you can invert in order to get the angular rates in terms of the angular velocity measure numbers. That is, you get the dotted quantities in terms of PQR. And there is a singularity. You see that in this it doesn't seem like there is a singularity, because only cosines and sines are involved. At the most you get some term going to 0. But now if you are trying to invert this particular matrix, then you see that there is going to be some of these terms are going to be 0 in the diagonal itself. For example, here itself you can see that when phi is equal to 90 degrees, you see that cosine phi becomes 0, and you have on the principal diagonal a 0 term. So obviously that's going to be a no. So there is a singularity, and I already said, warned you that this is the case with most finite rotation representations, and one way of overcoming them is to essentially avoid those or bypass those in some way, and which is what is done at theta equal to 90 degrees as well, for as the other example, other than phi equal to 90 degrees. So essentially you stay away from it, or you just work around that, or you make a change of variables when you come to that particular position. So there are very many different numerical techniques in order to take care of this, but at the level that we are studying this course, it's just enough for us to be aware of this fact that there is a singularity, and so you should account for it. Now, I already said that when you have the luxury of small angles, then yes, the finite rotation becomes an infinitesimal rotation, and then you can have vector representation of that, which is what we will see in this particular slide. When we say small angle, we want all those three angles that we rotated it by, that is xi, that is theta, that is phi, or that is the yaw, pitch and roll. All of them have to be very small angles. If it is the case, then this general set that we had for large angles, we can reduce that. What do you think is the process in order to go from large angles to small angles? What is the first approximation you can do? Exactly, right? So if you're looking at expanding these in power series, the sines and cosines, you know that the first term in a cosine series is 1, and the first term in a sine series is the angle itself, right? So all your sines will become that angle of whosoever sine it is. So sine phi would become phi, sine phi would become phi here as well, and sine theta there would become theta, and the cosines would all become unity. So obviously this becomes a much simpler set of equations that you have here. But you still see that there is a level of nonlinearity that is there, which is a quadratic nonlinearity. Xi theta over here, that you see theta phi over here. But you know that if it's a small angle, then the products, and remember that we don't care whether it is having a dot or not, because essentially they are unknown quantities. Phi theta xi are unknown, so their dots are also unknown. So essentially it's a combination of two unknowns, and when you have a product like that for small quantities, both those products will all go to 0. So which means that we'll drop off all the quadratic terms and retain only the linear terms. Essentially it's a linearized version of that equation, and then you see this is what you had as an intuition, that P, which is the roll rate, is equal to the roll angle's derivative with respect to time. Your pitch rate Q is nothing but the pitch angle's derivative with respect to time, and your finally your yaw rate is nothing but the yaw angle's time derivative, which is quite intuitive, but that is valid if and only if the small angle approximation is there, which we take in two steps. One is replacing the trigonometric functions by their power series and retaining the first terms, and then dropping off the quadratic terms, or in fact all the nonlinear terms, which only are quadratic here because of that first approximation, and therefore eventually you're left with only the linearized terms. Then yes, P, Q and R are fairly simple, and you can represent your rotation as a vector now, phi about B1, theta about B2, and xi about B3, and then I can take a time derivative of that. B1, B2, B3 are constants in B if I'm taking the time derivative in B system, and only phi, theta and xi change, and their dots is what you're looking at, and which is what we had defined as PQR in the angular velocity vector. So a simple relation between the angular velocity measure numbers, which are your PQR, and the angular rates, which are your phi, theta and xi. Okay, so now we have already introduced this concept of direction cosine matrix. We would like to just talk a few things about its properties and how we can utilize in other things than what we already showcased it. As I said, I'm abbreviating in all the slides the direction cosine matrix as DCM, and many people, many books utilize the symbol C for the DCM because cosines are involved. So matrix C, which is a 3 by 3 matrix, is typically called as a direction cosine matrix. but some other books call it as a transformation matrix because you're transforming from one system to another system. So they will abbreviate or denote the direction cosine matrix with a T for transformation. Similarly, some other books might call it a rotation matrix and therefore use the notation R for rotation in order to denote the same thing. But essentially, it's the same quantity that we are talking about, whether it's DCM represented by C, transformation matrix represented by T, or rotation matrix represented by R, are three different names for the same entity. Okay, so for any two dextral sets, by which we mean a right-handed orthogonal system of unit vectors, then you have the direction cosines can be defined in a way which is seems to be slightly different from what we did, but it's essentially the same thing. That it's a 3 by 3 matrix T, and if you have to populate it, you have to take the values of the rows and columns one by one, each case going by from 1 to 3, so total of 9 elements. Already we noticed that in the example that we did, it's not necessary for it to be symmetric or antisymmetric, which means each one of those 9 elements have to be obtained. Okay, they are in general independent of each other. That's what it seems like. But we know that all of these are in terms of just 3 angles, which are phi, theta, and xi. And in fact, the way we have described it, it was just in terms of 2 angles. Xi was not figuring in the direction cosine matrix that we had. So in the most general case of any arbitrary angle of yaw, any arbitrary angle of pitch, any arbitrary angle of phi, large values, you still saw that the direction cosine matrix did not involve xi. So it is possible that you can get the direction cosine matrix just in terms of 2 variables if you do this sequence in an appropriate way, which is what helped us to have it in that particular form. But irrespective of what you have, if you have arbitrary 2 sets of unit vectors, both being right-handed orthogonal set of unit vectors mutually perpendicular, then you take the dot product, you have vi dot aj is equal to tij. Now, is the dot product commutative? Yeah, it is, right? So if I interchange this, I should get the same value, right? aj dot bi. But then why do we say tij is not symmetric? I'm saying that the dot product is commutative, okay, which we all agree, right? If it is commutative, then I can put it the other way around and I call it aj dot bi, okay? So, but I know that for a fact that I've seen an example already that T is not a symmetric matrix. So I'm just saying, what is the paradox over here? It's the same, yeah. I'm asking why isn't T symmetric, which means I'm asking why isn't Tij equal to Tji if the dot product is commutative, which it is. Yes. Not necessary. See, essentially, because cosine is what is involved. Cosine of negative theta is same as cosine of positive theta, right? Exactly, exactly. So you're essentially looking at going from I to j or j to I, as Gracie pointed out. It involves a particular choice of I and j already for this particular equation. So for example, if I'm looking at T12, it has to be B1 and A2. It cannot be B2 and A1. Okay, which is why if you have that, then you would have T21, and the unit vectors involved itself are different. So even if I'm reversing them, it's two different unit vectors that I'll be dealing with. Instead of between B1 and A2, I'll be dealing with A1 and B2. So those are two different unit vectors I'm taking a dot product of, and obviously in general you would have different answers for that. Yeah. So taking it forward, of course, yes, in terms of how the dot product is defined, it's the two vectors whose dot product you're taking, their magnitudes, and in this case both are unit vectors, so their magnitudes are equal to 1, the hatted quantities. So what you're left with is just the cosine of the angle between your bi and aj, whichever two unit vectors you're taking the dot product of, right? So angle between bi and aj, and that's what you see over here, because the first term has dropped off as 1 into 1, unity into unity, and that's you can represent that angle between bi and aj as theta ij. Don't confuse this theta with the pitch angle that we talked about. That's a different thing. We're talking about this in a very general sense. Between two bodies, you're talking about the theta angles over there, which is the angle between bi and aj. So in a sense, this theta aj will somehow inherently contain all of these three angles, because there are essentially 9 of them. So I and j taking on 3 and 3 values each, 1, 2, 3. Okay. So to write it out explicitly, of course, your direction cosine matrix, because we are dealing with 3D problems, so essentially it's a 3 by 3 matrix, and we have it in this way. The first index is always, remember, the row number, and the second is the column number. It wouldn't have mattered if it was symmetric, because then T12, for example, was equal to T21, but here they are not, so it's very important to always recognize that the first index in this case also, I is the row number and j is the column number. So this particular direction cosine matrix, even though I'm just writing as T because we had just two frames of reference, namely A and B, but when you have more number of frames of reference, it's important to specify as a superscript or some way that what is the transformation taking place between. For example, here also we had two intermediate frames and one initial and one final, total of 4 frames. So then you can't just talk about a T. You have to talk about one level of T here, another T here, another T here. So you have 3 levels of transformation taking place to get the total whatever is happening over there between those two, from the initial to the final. So in that case, it's very important to specify what is the transformation taking place between what frame to what frames, from frame A to frame B. Okay, so it's how do you get B starting from A. So that's how you read this, the way it is written in most textbooks. So the direction cosine matrix notations and sign conventions will vary, so don't get confused. So there's one in your textbook, there could be something very different in some other textbook and some other research papers, etc. Sometimes this notation, I said this, the way we write it is for the how to get from A to B, but some people might write that as A/B rather than as B/A. So just be very clear about whichever book you're reading, what is the convention it follows. And also in terms of the signs that are involved, what is positive for one might look like negative for the other, so just be aware of these things. Okay, sometimes the transpose of T is called as that. So in other words, here we are going from A to B, instead going from B to A might be called the transformation matrix, so just be aware of that as well. Okay, so then as I said, these are 3 different names for the same entity, whether you call it DCM, rotation matrix, transformation matrix, they're all one and the same. And as I said, instead of T, sometimes books use the symbol C or the symbol R for it, in which case you would find these kinds of notation also. Sometimes instead of putting both as post superscripts, you might see one is a pre-superscript and the other is a post-superscript, going from A to B. So this is also a very common notation that is used in a few books. Coming to the rows and columns of the direction cosine matrix, we can see that once we have this, you can see that any vector for that matter, first of all, can be represented in terms of its in any particular frame of reference. For example, if I have an arbitrary vector v and I want to represent it in frame A, in which I have introduced already coordinate system and also the tangential unit vectors as a1, a2, a3, then to get to the measure numbers of each one of them, I just have to dot it with the corresponding unit vectors. To get the a1 measure number, I have to dot v with a1. To get the a2 measure number, I have to dot v with a2, and similarly to get the a3 measure number, I have to dot v with a3. So this is the general definition that you are aware of for all vectors, okay? Where essentially you are projecting that particular arbitrary vector onto the three different directions, a1, a2, and a3 hats. Now, for the unit vector in the b-axis system, you would have similarly, if you're looking at instead of v, you take this example, since that is valid for all vectors v. The special case is if I choose v as b1. So then you see that instead of v on the right hand side also, I have replaced the first term within the bracket in all three terms as b1. Okay, instead of v, we have b1 here, and b1 here, where v was there in the first equation. Okay, so when we do that, then we recognize from our definition of the Tij that any b dot a is essentially the corresponding t element of the transformation matrix. So I replace the 1.1 with t11, the 1.2 with t12, and similarly your 1.3 with a t13. Okay, so then you see that this is another way of looking at the same thing, which is quite obvious, because if you're looking at the way we wrote the matrix representation of that, that's what it would have anyway gotten into, right? So because we are writing b1, b2, b3 in terms of a1, a2, a3, or vice versa, depending upon which we were dealing with, which kind of rotation we were dealing with. So essentially each row should essentially give this to us. So in other words, what the direction cosine matrix row is giving is, that is whether it's the first row, second row, or third row, each row is giving us the measure numbers of b unit vectors, because in this case, for example, it's giving b1. Similarly, the second row will give you b2, third row will give you b3, right? So each row of the direction cosine matrix, whether you call it T, C, or R, the first row is giving you b1, second row is giving you b2, third row is giving you b3, all in terms of the with respect to which the rotation T represents, namely A in this particular case, because it's rotation of B in A, and therefore these are measure numbers along A1, A2, and A3, or in other words, you can call this together as a component. The first component is T11 A1 hat, second component and third component that you have here. Okay, on the other hand, if you're looking at columns, it's like vice versa. So you're essentially getting your A1 hat, for example, in the first column in terms of B1, B2, B3. Second column gives you A2 hat in terms of B1, B2, B3, and so on and so forth, right? So because of the fact that this is orthonormal, as I said, which means that the transpose itself is the inverse, and therefore you don't need to actually take an inverse. You can directly use the transpose in order to do that, or in other words, transpose is nothing but interchanging the rows and the columns. The properties of the direction cosine matrix are essentially that orthonormality property that we talked about. So going from A to B or B to A, essentially you are using pretty much the same matrix transposed with itself. So essentially you're looking at the product of T and T transpose, because T transpose is unity, therefore that should give you an identity. The other way around is also true, that you pre-multiply. In general, you know that two matrices, if you're multiplying A and B, it's not same as B into A. If A into B is not equal to B into A, okay, in general, for matrices. But here you see that that is valid, because both are going to give you the identity matrix. So essentially, because you're essentially getting that identity matrix, its determinant is equal to unity, 1. Therefore, we call this as normal, and you typically represent that as this, the determinant of that particular matrix essentially is a positive 1, and it's essentially orthonormal, because normal because it involves essentially unit vectors, and orthogonal which are perpendicular to each other. So it's the fact that the unit vectors themselves were orthogonal and unit vectors which is having a magnitude of 1 each. Therefore, it's essentially unitary, in which case you don't need to go through the long route of finding the inverse. You can just transpose or interchange rows and columns in order to get to it, which also means that this is essentially a non-singular way of representing. So remember that we already have one way of representing in going using these three angles, okay? That is xi, theta and phi. So in that approach, we saw that there is a possibility of getting into singularities, etc. But here, when you have that transpose itself as the inverse, then there's no difficulty in taking the inverse. So that is the whole idea, that essentially you have a non-singularity. But there's a disadvantage that you have 9 terms to deal with. A T matrix is a 3 by 3 matrix. It's not symmetric, it's not antisymmetric. So you have 9 terms to deal with. Of course, there are some ones and zeros, but essentially you have 9 terms to deal with. But in this approach, I needed only 3 guys, xi, theta and phi. So I have lesser number of things to deal with, but complications are there. This is more number of things to deal with, but a simpler way to handle with this, with the matrix manipulations, etc. Now coming to the transformation of the unit vectors, just repeating what we already had, that the B system is given from the A system by just pre-multiplying by TB/A, and you have the other way around as well, TA/B, giving that, and yeah, there are many different ways of representing the same thing, because A/B can be represented as B/A with transpose, because that is going to give you the inverse of it. Okay, so all of these kinds of things might seem obvious, but sometimes it's useful when during derivations to utilize some of these for manipulations of the equations, the matrix manipulations that you can do in order to arrive at required results. So then continuing with that, coming to the measure numbers. So in a 2-axis system, measure numbers of vector v in a 2-axis system would be given by v subscript ai and v subscript bi, and like it is for any expansion, you just have to dot it with the corresponding unit vectors. For the big A, it is the small ai vectors, and for the big B, it is the small bi vectors, both with hats to represent their unit vectors. Okay. Now there's a column matrix way of representing that. Like many of you have been using angular brackets to put those 3 measure numbers for vectors. So similarly, you typically use a column matrix in order to do that. So in B or in A, it's the same vector v, but the actual numbers will change whether you're putting it in terms of the B system's unit vectors. What is the measure numbers along B1, B2, B3, as opposed to the measure numbers along A1, A2, A3, and that for that also you can actually utilize these transformation matrix in order to go from one to the other. If you know V's in a A system, all that you have to do is to multiply by the transformation matrix in order to get it in the B system, and vice versa. All that you have to do is a transpose instead of a actual inverse. Coming to simple rotations, you have simple rotation theta about the axis A1 hat equal to B1 hat. Then in that case you would have T1 of theta. So remember that we just stopped or paused our notation theta to be the pitch angle. Here we are talking about any general rotation between 2 sets of unit vectors. So that's what we are talking about here. Here we are talking about a rotation about 1. Don't confuse it with a roll, because roll we are talking as phi. Okay, so here it's not for an aircraft but any general bodies, because you'll see a few examples that you're going to be solving are non-aircraft examples as well. So don't always harp upon these particular notations of xi, theta and phi. Okay, so this is what we would have for the transformation if there is an angle of rotation theta about the axis 1, which is A1 or B1, okay, because that's going to remain constant through that rotation. A1 and B1 are not going to change. It's only A2 and B2 which are going to change relative to each other. So similarly, if you're the notation for that is because it's about the axis 1, so T subscript 1 by an angle theta. Okay. Similarly, if it's about the second axis, by the same angle theta, let's say, then you write it as T2 subscript of theta. And about whichever axis about which you're rotating, that particular row and column become very simple. So here you see it's 1 0 0 1 0 0, okay, because those two are equal to each other, right? Because A1 and B1 will be the same. In this case, the rotation is happening about 2, so your A2 and B2 will be equal to each other, which means that the second row and second column will be the simplest. It will just involve a diagonal term of 1, or all the off diagonal terms will go to 0 in those rows and columns, okay. The rest will of course involve the angle, sine and cosine. Then similarly, finally you have the third row and third column being simple, because the rotation is happening about either B3 or A3, which are both the same way of saying the same thing, and the angle once again is theta. Then you have this kind of a rotation. So this is what simple rotation involves. So we had introduced this as a concept where we said that the axis of rotation is such that between those two bodies it remains a constant, okay, it doesn't move with respect to those two frames of reference, whose rotation with respect to each other is what we are interested in, and therefore this is as far as the direction cosine matrix for that concept of simple rotation is concerned. Now coming back to aircraft flight dynamics, now those were all generic things. Now we are talking about once again this 3-to-1 rotation, the rigid body, and we want to utilize that concept that we just introduced, but now we have 3 rotations, so we have to go in 3 steps. Okay, so I'll go from the bottom up. So essentially you're going from the A system, so because you're initially aligning the aircraft with the earth fixed system, and you want to get to your B system, which is the body fixed system. So essentially first you're multiplying VA with T3 of xi, that is the yaw, so that is in the 3-to-1 system. Once that is done, you have reached this particular thing, then which is the blue thing, and from that you want to go to the next step. You have to pre-multiply by T2, but this time all these angles that we are talking about in the previous slide, we were all putting everything as theta, 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 okay. So here we are saying no, about 3 it is called xi, about the intermediate 2 it is called theta, and about the intermediate 1 it is called phi, okay. So once we do that, it's essentially 3 matrices, each of which are 3 by 3 transformation matrices that you're multiplying, pre-multiplying VA with, you will end up with VB, okay. That's quite straightforward, but essentially how that process happened is in those 3 steps, which is what is illustrated by the first 3 lines of the equation, where you're going not directly from A to B, but via B double prime, first B prime and then B double prime, which is what you see in the first 3 equations over there. Okay, for an aircraft with the rigid body 3-to-1 orientation angles, so that's essentially rewriting this thing and saying that what is multiplying VA is nothing but this transformation matrix and going from A to B, which is just the product of 3 direction cosine matrices, each of which is for a simple rotation, but those simple rotations have happened about mixed basis. It's not about the same basis that it has happened. One has happened about the B basis, another has happened about the B prime basis, this one has happened about the B double prime basis, but essentially you can use that to get to from the initial to the final orientation. Okay, any doubts or questions about this so far? Orientation angles are clear, application to aircraft rotations are clear. Okay. Now we get on to something which is very popular in the dynamics literature, especially in basic books, the Euler's second law, which we have already looked at. Remember that Euler extended Newton's work from particles to centers of masses of rigid bodies for translation, and then also brought in the rotation. The first law took care of translation, the second law takes care of the rotation. So here we are going to revisit that second law and look at a few alternate forms of that. Okay, so we already know Euler's second law, but whatever we studied in this morning in terms of various aspects of the angular velocity, we want to bring that into picture. Already we have introduced the concept of angular momentum h, so we are going to look at its the form of E2L in AM as well, apart from AV. And all of this we are going to do for not just simple rotations, which was just 2D, which is what we saw earlier, but now we are going to look at it from a 3D perspective. And most of what I'll be talking about here, you can see is being covered in your textbook in sections 7.2 to 4. Okay, so we had already introduced, for example, this IZZ, I subscript ZZ, as the moment of inertia about the Z axis, about a particular point, and we put that as a superscript C, for example, and then we calculated that. But that is just one entity or one element of a 3x3 matrix, and we want to look at the matrix as a whole, which is what we call as the inertia matrix, and for 3D, of course, it's a 3x3 matrix. So just recollect that the equations of motion, irrespective of whether you're dealing with 2D or 3D problems, involves two aspects, because we are dealing with rigid bodies now, no longer looking at just particles. So whereas particles are needed only translation, rigid bodies need translation as just like particles, but in addition they need rotations as well. Okay, now let's look at the angular momentum form of this. That is, you're looking at the sum of all the external forces causing a moment m about a particular point P, and if you algebraically sum up all those moments, those are the external moments or the resultant external moment acting on the body, that should be equal to the time rate of change of the angular momentum. But if P is any arbitrary point, then it doesn't work. We saw that it works only for two special cases, where P is either the center of mass or it's a point in an inertially fixed frame of reference. Only for those two cases it happens. In other words, we generally represented those points as C and O. C referring to the center of mass of the body, O referring to any point which is fixed in an inertial frame of reference. Only for those you will have it equal. But for a general point, this of course is still valid, because this is essentially looking at the mass times the acceleration on a small element, infinitesimal element of mass dm, and essentially you're taking that position vector crossed with that. These are vectors, of course. R should have a vector sign just like A. Okay, now the second law for particle set or rigid body is simple in terms of angular momentum about a point fixed is simple only for two cases. The first case is a point which is fixed in the inertial frame of reference, where we said that it is the summation of MO, that is the moments about the inertially fixed point O, is equal to I d by dt of H naught, right? So because H naught is the angular momentum about an inertially fixed point, and some examples of that are a pivot point which is fixed in an inertial frame of reference and rigid body, but not its center of mass necessarily. Example, any point which is on a fixed rotation axis, not passing through the center of mass, because the center of mass is already taken care of in the other thing that we have, for which also it is anyway valid. Okay, so even if it is not center of mass, as long as it's it's either a pivot or a part of the axis of rotation, then it is still valid. Okay, and these two angular momenta are related to each other. That is, if you have the angular momentum about the center of mass, you can get about the inertially fixed point by just using the translational momentum L and taking the pre-cross product from O to C. Okay, so this is something that you should remember. Usually for the velocity relation that we were looking at, we are going from the known to the unknown quantity. Here it's essentially coming from the position vector going from one to the other, and therefore you see this is ROC, not RCO. This is one thing that you have to remember. And therefore the second law, though it can be written in simple forms for these two sets of points, of course one is just a single point, that's a set of points. In both those cases it can be written that way, but here it cannot. So just be aware of this. Don't use it for cases where it is not the center, neither the center of mass nor the inertially fixed point. Now the rigid body's angular momentum about the center of mass, again this is a relationship that we have had before. So some of these things are kind of revision because we need that those equations for some of the derivations we're going to do in terms of the angular velocity. We want to get E2L, that is Euler's second law, which relates momenta and angular momenta in terms of the angular velocities, but we already had it in terms of angular momentum, which is what we are quickly revising. Okay, so we saw that it looked somewhat similar to the centripetal acceleration, but instead of 2 omegas and 1 r, it is involving 2 r's and 1 omega. That was the term that we had identified over there. That is about the center of mass, the angular momentum about the center of mass. How did we get there? So if Q is a point within that infinitesimal mass element dm of the rigid body, then in the limit you see that your angular momentum about C is just nothing but the position vector crossed with the translational momentum, and the translational momentum is nothing but mass times velocity, which is dm times vq, and which is of course calculated. So, and again for this particle or the infinitesimal mass element q, we can write the velocity in terms of the center of mass's velocity with just an omega cross rcq as the difference term between the two. This is of course valid for any 2 points fixed on the body, and therefore for C and Q as well. And therefore you see that if you substitute for this expression for VQ, you substitute over here, then you see that one of the terms drops off, and we said that remember that neither VC is going to 0 in general, neither RCQ is going to 0 in general, neither are they parallel to each other, but because of the fact that VC is constant and comes out of the integration, and the integration is left with RCQ times dm, that integration is the definition of the center of, by the definition of center of mass, has to go to 0, right? So which is why that term dropped off and you are left with only this term. So I'm going through all of this quickly because it's just a revision of what we have already done. So that's the center of mass definition, which resulted in the angular momentum about the center of mass being this simple expression of two double cross product, integrated of course. So now about the center of mass, they were continuing the angular momentum expression if you are going to expand that out and write. So this is a very, looks very compact and simple, but for a numerical calculation it may not be good enough. You have to actually expand out your RCQ, expand out your omega, and expand out our RCQ, the typical ways in which you have taken the cross product. Once you do that, you will see that the omega is for the body. It doesn't matter which particular elemental mass of that body you're considering. So eventually once you substitute that there and expand it out, the omegas will come out, and what will be left are some kinds of r squareds that are involved, okay? And those r squareds are going to essentially contribute to your mass moments of inertia, because the weightage involved is the mass, which you will represent of course by rho dV, the mass density rho times the volume element. And once you do that, you see that essentially you are ending up with, of course we had done for a 2D problem, and where we had dealt with an IZZ kind of term. So this particular term we are already familiar with, this last term that you have here. But you will get a similar term in the XZ plane and in the YZ plane as well, right? And similarly they are going to get coupled with each other. And so just like you have mass moments of inertia, you are going to have mass products of inertia. So these are going to result in the off diagonal terms for you in the matrix when you are going to write the 3D inertia matrix. So essentially this is what it comes out. And of course in calculating this particular double cross product, we have expanded out all your r's in terms of x, y, z's, and also your omegas in terms of omega x, omega y, and omega z, okay? And of course it's for a particular unit vector system in which you are expanding b1, b2, b3, the body fixed frame of reference, right? So you might as well done, this is a generic vector equation, you could have expanded it about A or any other frame of reference, just that this helps to have it in the body fixed frame of reference. Then you have this simplification. Okay, so how to get to that? Very easy. Your position vector of any arbitrary point Q of the rigid body B is given with respect to the center of mass C by just x, y, and z, because It's a frame which is fixed to the center of mass as the origin. So therefore, going from the origin is equivalent to going from the center of mass to an arbitrary point Q, and arbitrary point is identified as x comma y comma z along b1 hat, b2 hat and b3 hat respectively. Once we do that and substitute that into the equation we had in the previous slide for the angular momentum, along with of course your omega, or what we have written here as well. So all that we have is we need two of these quantities because one is repeating. So we already have an expression for RCQ in the first equation on the slide, and now an equation for omega also can be written in the body fixed frame along b1 hat, b2 hat and b3 hat. It is omega x, omega y and omega z, the measure numbers. Once we substitute and take the cross products, this is essentially the expanded form of that. Okay, so let's continue with that. Now these are the angular momentum terms, the coefficients of the angular velocity. If you look at all of these are coefficients of omega x, because omega x is not dependent on dm. It's a body property. It can be taken out of the integration. So essentially you're having these three terms only. Similarly for omega y and omega z. So this can be written as a matrix equation multiplying omega x, omega y and omega z as a column matrix. So once you have that, you will see that this angular velocity hc in the B system, hc1, hc2, hc3 along b1, b2, b3 can be written in a very, very simple form. Before we do that, we introduce these concepts. In fact, it's just extrapolation of what we had already introduced. This is something that we have been dealing with. We have even used this to calculate for some problems, etc. So IZZC we are familiar with because we were dealing with 2D rotations, simple rotations in that particular case. Now we have just expanded it out into 3D rotations, and therefore just like IZZ, we have IYY, IXX. All that you have to replace is when it is ZZ, other than Z, the other two come in, x squared and y squared, right? Similarly, when you have y, there's no y squared involved. It's x squared plus z squared and so on and so forth, right? So all those three are there. Similarly, this is something that we had not seen before. It's equivalent to the mass moment of inertia. In other words, it has the same dimension, it has the same unit, it comes from a similar source, but we are talking of products now of yz, xz and xy, and they all involve a negative sign in order to take care of these negative signs that we get automatically from this double cross product. Okay. So these are what you have on the left side. Here are the moments of inertia, mass moments of inertia to be more precise, rather than area moments of inertia, which are also used in other subjects in aerospace engineering. Here we use essentially for dynamics the mass moment of inertia that you should be familiar with, and what you have on the right hand side on the top three equations are the products of inertia, mass products of inertia. And both of these are about the center of mass, which is why you see that superscript c. So if it's about any other point, you would have different values, but typically for any other point we use the parallel axis theorem in order to calculate those. We typically get to this either from the table, or if it's not given in tables, then we have to calculate it as an actual integral over here, but we don't need to do that for every point. Once we have this, we use the parallel axis theorem to go to any other point, because we know the distance between the center of mass and that point about which you want to take the angular momentum, and therefore you will use that distance squared times the area or the mass in this case, because it's a mass moment of inertia, and therefore you will get to the I, not necessarily about C, but any arbitrary point P. Okay, now the angular momentum in terms of the inertia matrix, essentially utilizing those new definitions that we have introduced for these three principal diagonal terms, namely the mass moments of inertia, and the off diagonal terms, which are the products of inertia, mass products of inertia, all about C. And that matrix is just multiplying your omega x, omega y, omega z, the measure numbers of your angular velocity in the B frame, that is the body fixed frame. And this is also in the body fixed frame. You have hx, hy and hz, the three measure numbers of the angular momentum about C, the center of mass, is given by this simple expression. The angular momentum measure numbers along the rigid body axis are of course given as this: hxc along b1 hat, hyc along b2 hat, and hzc along b3 hat, algebraically added to each other. And this is the new matrix that we typically have. Now you don't need to put xx, yy, zz as subscripts because they're all taken care of within the matrix. So whereas these are all scalar quantities, this is a symbol for a 3 by 3 matrix which involves all those constants, which is a constant for a given rigid body, and of course a particular set of xyz axes that you have chosen. If xyz are chosen in a different orientation, obviously the values of this are going to change even for the same rigid body, even about the same center of mass. So it depends both on center of mass and the choice of your xyz coordinate system. So on the previous slide, of course, we had this: the angular momentum measure numbers in the rigid body axis can be written in terms of the angular velocity measure numbers of the rigid body axis. So these are the angular velocity measure numbers, these are the angular momentum measure numbers. So in other words, AM and AV, angular momentum and angular velocity, are related to each other, and the thing which binds them together is this particular matrix, which is the inertia matrix. Okay, we didn't have that as the end goal. We wanted to go a step further and get the moments related to that, because typically we saw forces, that rate of change of translational momentum. A similar argument was for the moment, which is due to the forces. That moment is essentially coming from the rate of change of angular momentum. So that is what we are trying to get to. So that involves typically two terms. One is quite obvious, that is essentially I, if its I is constant, and then you have the omega dots. So this is like saying that you had the force is equal to mass into acceleration. That is the translational version of that. This is the rotational version of that. Instead of force, we have moments, external moments that are acting on the body, and resultants of that about x, y, and z. And then you have the inertia matrix instead of the mass. So this is the important thing to remember, that whatever role mass was playing for translation, the same role is being played by this inertia matrix for your rotation. And then of course, instead of velocities, translational velocities, Vx, Vy, Vz, you now have angular velocity, the accelerations, which is Vx dot, Vy dot, Vz dot. We are having the angular accelerations alpha x, alpha y, and alpha z, which are of course equal to the corresponding omega dots. Okay, but that's not all. In the case of rotation, whereas in translation we'll be done with it, force is equal to mass into acceleration. Here we have an additional term which is coming over here, which is essentially your centripetal acceleration that is there, which is omega x, omega y, omega z crossed with this particular quantity, which is the inertia matrix times omega. So which is nothing but again your h, which essentially this is I omega is nothing but h. So essentially h about c, and therefore you're crossing your omega with hc. That is the additional term that you get. So how do we get to this? So the moment resultant about the center of mass, the external, because the internal are all cancelling each other out, that we had used the Newton's third law, remember. So these are only the external moments about the center of mass acting on the rigid body. Okay, so that's equal to I d by dt of hc, because it's valid for center of mass and inertially fixed points. Here we are using for center of mass. So then hc, because it's the d by dt with respect to I, we can break it into d by dt with respect to b, the body fixed frame, and then additional term, which is the angular velocity of b and I crossed with the vector whose time derivative you are taking, namely hc, the angular momentum about the center of mass. So the representative, we can represent the applied moment in the rigid body axis measure numbers. So in other words, your MC that you have can be expressed as measure numbers along B1 hat, B2 hat, and B3 hat, which is nothing but the x component, y component, and z component. So the measure numbers are mxc, myc, and mzc. So once again, it's about the center of mass. So when you do that, and you substitute into the equation that we had in the previous slide, we end up with this particular equation that I described to you in the beginning of the slide, which is called as Euler's dynamic equations, a very popular set of equations in dynamics, basic dynamics, where you're looking at the correlation between the external moments that are applied along xyz, which are body fixed, with the angular velocities about the same set of axes, body fixed axis xyz. So that correlation has two terms. One is the centripetal term and the other is the conventional term of the moment of inertia times the angular accelerations. So here remember, there are no angular accelerations. Even if you had all angular accelerations equal to 0, you could still have a non-zero moment. So that is an important thing, because remember from the very first law of Newton's law of motion, you know that a body remains in a state of rest or of uniform motion if there is no external force acting on it. If you try to convert that for external moments, you could fail, because even though this term could be 0, you could still have this particular term. So in other words, angular velocity remains constant. Angular velocities are not changing, which means angular acceleration is not there, but still you could have external moments which have to balance out this particular centripetal term. So that's an important thing to remember. Okay. Next, all terms are in the rigid body axis, that is the small b1, b2, b3 system, which is fixed to the frame B, which is nothing but the rigid body itself, but it's a non-linear ordinary differential equation. Why is it a differential equation? Because dots are involved. Okay, so it's a first order differential equation because the dots are involved. Second term does not have any derivative, but it has a complexity that it's a non-linearity because there are omega squareds. Omega is an unknown. Just like omega dot is an unknown, omega is also an unknown. So whenever you have either the derivatives or the unknown itself in powers other than 1, then you are essentially having a non-linear equation, which in this case is a second degree of non-linearity because quadratic terms are involved. So it's a non-linear, or rather quadratic to be more precise, ordinary differential equation. Okay, now we look at the rate of change of the angular velocity, because we remember we already have omegas, we want to get to alphas eventually. So the rate of change of the angular velocity, which is the angular acceleration, once again in the same set of unit vectors b1, b2, b3, we want to get the measure numbers, which means that eventually what we are going to say is that the angular velocity can change, that is non-zero angular acceleration, even with a zero applied moment. In the previous slide, one of the interesting things that we observed was, in the presence of moment, there is a possibility that there is no angular acceleration, only angular velocities are there, constant angular velocities. But there's another a corollary to that we are seeing over here, that when you have zero moment, it is still possible that the angular velocity can change, because there are two terms on the right hand side. Both need not go to 0 simultaneously. One can be positive, other could be negative of the same value, and essentially they are cancelling each other out. Okay, so in the previous slide we are just repeating that particular equation, that is the Euler's dynamical equations. This is the relation between the moments and the angular velocities and their rates. And if you invert this particular equation, you want to get omega dots, all that you have to do is to take this entire second term to the left hand side, and once I do that, this positive will become negative, which is what you see over here, and then I'll have to invert this matrix and multiply by that in order to get omega dots. So I just want to get the omega dots in terms of the applied moments. Here I am having applied moments in terms of omega dots. I want to get it the other way around, which is what this particular equation is. You see that this is the inverse of the inertia matrix, multiplying this difference between the two terms. One is the external moments, the other is omega quadratic with the inertia matrix in between. Okay, so this is a very clear case where you see that in this particular case, if you have a non-zero, you can have a non-zero angular acceleration even with zero applied moment. So in other words, if I'm not applying any moments on this body, mx, my and mz about c are all equal to 0. Okay, so even though I have that as 0, I still have one term here, because of which it is possible that your omegas are changing, and in other words, omega dots are non-zero. Okay, in other words, you have angular accelerations alpha x, alpha y, and alpha z, which is possible. So this is kind of counterintuitive when we are coming from Newton's first law, but that is valid, remember, only for forces and translations. Here we are talking of rotations, and therefore this new possibility is there. Okay, a few more things about that 3D inertia matrix that we already introduced. There's this the products of inertia that we introduced, just like moments of inertia, which are on the principal diagonal. We had the products of inertia on the as the off-diagonal terms. Remember, they were calculated as negative of xy times dm, negative of yz times dm, negative of zx times dm. So those kinds of quantities, and we are going to talk about certain symmetry associated with that, because x into y can also be written as y into x, etc. That's essentially what you're talking. Therefore, your inertia matrix is actually symmetric. So the product of inertia about the center of mass is equal to 0 for any rigid body or its parts if, under certain conditions, either or both axes represent the product of inertia forms essentially you're looking at a plane of symmetry. So those axes which are going towards calculating a particular product of inertia, let's say you're calculating integral xy dm with a negative sign, which is nothing but your ixy about the center of mass. So when you're looking at that, then you see if that xy formed a plane of symmetry, then essentially that is going to go to 0. Okay, so that is because there are positives and negatives on either side of the plane of symmetry which are going to cancel each other out, and that's what you would see happening over there. So you can take advantage of situations where you have certain planes of symmetry in the rigid body. So if you have just one plane of symmetry alone, like you have in the case of the aircraft, you know that the xz plane is a plane of symmetry. That's the x-axis is passing through the length of the aircraft through the nose, and the z-axis is downward. So essentially that xz plane is a plane of symmetry. One side you have the port, the other side you have the starboard, right? So when you have something like that, then two of the products of inertia will go to 0. That's in the case of the aircraft. Okay. Now, on the other hand, if you have two planes of symmetry, like let's say a cuboid, for example, or a sphere, when you have infinite planes of symmetry. So whenever you have two planes of symmetry, all the three products of inertia will go to 0. In other words, it will become a diagonal matrix. Your inertia matrix will have only the principal diagonal terms, and therefore it's a diagonal matrix that you will have, and that's an example of that is a rocket. So a rocket engine, even if it has solid boosters, you know that it has at least two planes of symmetry, typical constructions, and therefore you have the all the three products of inertia going to 0. Okay, so this is an interesting thing. It's not that if you have one plane of symmetry, only one product of inertia goes to 0. If you have one plane of symmetry, two of them go to 0. When you have two planes of symmetry, three of them go to 0. So there's no advantage when you have a third plane of symmetry or an infinite planes of symmetry as in a sphere. There's not going to be much of a difference, because already you have a very simple case where you have only the principal diagonal terms, no off diagonal terms. So we saw the simplicity in the case of aircraft, and in the case of the rocket, we need to utilize that when we are dealing with aircraft rigid body dynamics or rocket rigid body dynamics. Okay. Next, we're going to look at generalizing the parallel axis theorem. Remember that when we introduced IZZ, we introduced the parallel axis theorem, where we just added d squared times the mass. Now we are going to do that for all the terms, whether it's a moment of inertia or product of inertia, right? So if it's the product of inertia, already we have done for the moment of inertia. For the product of inertia, this is how it looks like. Remember, for the moment of inertia, it was zz over here, and it was a positive term, and it was mass times d squared, which is the distance between those two points C and P. Okay, here it is negative, because remember that the product of inertia itself has a negative in its definition, and then of course again it involves the same quantities in the product of inertia, namely x and y of that particular point P with respect to C. Of course, C is the origin. So xp and yp are the distance along the x and the y axis of the point P from the center of mass. So that multiplied by the mass is going to subtract. So In this case, whereas there we said that m is positive, d squared is positive, and this is positive, therefore it's only going to add, and so you had the minimum value about the center of mass, everything else is going to be more. That's valid only for the mass moments of inertia, not for the products of inertia, because we don't know the signs of x and y. One of them could be positive, the other could be negative, or both positive, and then again you have a negative sign here, so you can't really say. So that what is for the center of mass would be either maxima or minima. You can't say anything specific about that. It's anything is possible. So generalizing the parallel axis theorem, are moments of inertia about 2 points related? Yes, they are. We already have related this IZZP to IZZC, and that is the equation that we had that I was just talking about, where you're having a additional term of mass, total mass of the rigid body times the distance between those 2 points C and P, about which you're interested in taking the mass moments of inertia about the z axis, right? So where d is the distance between those two z axes which are passing through P and through C, and therefore it's given as nothing but, using Pythagoras theorem, xp squared plus yp squared, the square root of that gives you d, where xp, yp and zp are the coordinates of P, the point P, with respect to C. So P could be any arbitrary point which is associated with that per same rigid body, as we said again, on, in, or with respect to. So our position, the products of inertia is about 2 points related. Yes, just like the moments of inertia are related about any 2 points, the products of inertia are also related, which I described at the beginning of the slide itself. So essentially this is a relationship between, for the product of particular product of inertia xy. Similarly you have for yz and zx, following the same rules. Instead of xp and yp you will have yp, zp, etc. Okay, now extending the use of the parallel axis theorem to a little more level of complexity, commonly used to find the moments of inertia or the products of inertia about the center of mass for a single rigid body composed of multiple parts. This is something very similar to what you use to determine the centers of mass and the mass moments of inertia already. Same thing can be done for the products of inertia as well. You can treat a very complex shaped body as made of modules, each of which are simpler geometry, and you can get those probably from tables, etc., and then you can add them up. Okay, so if the mass and the moment of inertia or product of inertia of each part about its own center of mass, because let's say a particular robo is made out of a sphere, a cylinder, etc., and then for the cylinder you know the values, for the sphere you know the values, and then essentially you are trying to bring it together for the entire rigid body, which is composed of those multiple parts. So if the mass and the moment of inertia or product of inertia of each part about its own center of mass, that is individual modules center of mass, is known, then the same thing for the overall center of mass, about the overall center of mass for the whole rigid body can be obtained as well. So how do you go about that? So assume it's made out of n parts, I running from 1 to n, then you just have to sum over that for each part. So each part about the center of mass of the entire rigid body is equal to about its individual center of masses, plus of course the mass times the sum of the squares. So this is something that you have already utilized. Okay, this is for the moments of inertia. But for product of inertia, it's just a parallel that you're using, very similar to that. And now that you have, instead of a plus, you have a minus, because there's a minus in the definition of product of inertia itself. And then of course you have mass times the corresponding coordinates depending upon which product of inertia you're taking. Because you're interested in xy, here you have xy over here as well. And of x and y of what? Of the individual centers of masses of that. So I gave the example of a sphere and a cylinder. So for the sphere you have a center of mass, for the cylinder you have a center of mass, and then you're trying to get to the center of mass of both. That center of mass of both put together is your C. for the cylinder alone is C1, for the sphere alone is C2, and essentially you're translating from individual parts to the whole body, where of course your XCI, YCI and ZCI, as I already mentioned, these values are nothing but the position vectors, measure numbers for the ith part's center of mass, namely Ci, with respect to the center of mass for the whole body, which is C. So we're using the same notation, C for both. One is without subscripts for the whole body, the other is with subscripts 1, 2, 3, etc. for the modules which make up that overall rigid body. Now there's a further extension, especially for those who are a little mathematically minded, for derivations, etc. We have talked about inertia as measure numbers, that is moments of inertia and products of inertia. Then we put them all together in a 3x3 matrix. We talked about an inertia matrix, but there's something beyond that from a fundamental mathematical point of view. Going from scalars to vectors, we said that we needed one direction. Going from vectors to dyadics, we needed two directions, and that's an example of a dyadic, a tensor of a second order. Just like scalars are tensors of zeroth order and vectors are tensors of first order, the inertia matrix that you just saw is a particular representation of a dyadic, which is a second order tensor. In other words, it involves two different directions. Okay, so the moment of inertia about any arbitrary axis n need not be b1, b2, b3, but some n making a certain angle with all three of them. Let's say that axis n. So then if you know I about, let's say, b1, b2, b3, which it could be any particular dextral triad that you have chosen, you can get it about any arbitrary n by just taking n transpose I n, where these n's are nothing but unit vectors along those desired axes. So for example, you already have a body B, you have introduced b1, b2, b3. Now you want about, you know the values of inertia about all three of them, both moments as well as products. Now you want about an arbitrary direction. You don't need to work from scratch. You can just use that inertia matrix that you already know, maybe from a table or a textbook. Then you just have to multiply it with n transpose n. Now this is equivalent of the what we just talked about in terms of parallel axis theorem. Parallel axis theorem is going from one point to another point. But at the same point, if you have a different direction, what do? That's where this comes in handy. So many a times you might know the inertia matrix at a particular, about a particular point in a particular direction, but you might want it about a different point in a different direction. So to get it about a different point in the same direction, you can use the parallel axis theorem. But to get it about a different direction, you have to employ this particular thing where you are pre-multiplying and post-multiplying by n transpose and n, where n is nothing but n dot b1, n dot b2, n dot b3. So essentially it's the components of or measure numbers of n along the b1, b2, b3. So if you are expanding out n along b1, b2, b3, what are the coefficients there? That's what is going to occupy here. And this transpose, of course, this is a column matrix, 3 by 1 column matrix. Once it's transposed, it becomes a row matrix, which is 1 by 3. So essentially you end up with that particular term INN. And of course, similarly, if you want the product of inertia about any two arbitrary axes, okay, n and m, again, n and m need not even be orthogonal to each other. Sometimes it might be useful to get that, okay, but most of the time for typical aircraft dynamics problems, it's usually orthogonal systems that you use. But whatever they may be, orthogonal or non-orthogonal, you can get the products of inertia I and m, where n and m are not equal to each other. If n and m are equal to each other, then what we have on the top is still valid. But if n and m are not equal to each other, then of course, inertia matrix still remains symmetric. Therefore, INM is equal to IMN, because inside only the products are involved. And in that case, it's very similar equation, but instead of both sides you are having n, one side you have n, the other side you have m. So, or you can put it this way, n transpose IM. So two ways of calculating the same thing, where n and m are the desired directions orthonormal vectors. So in other words, this involves m1 dot b1, m2 dot b2, m dot b1, m dot b2, m dot b3. Similarly, this involves n dot b1, n dot b2 and n dot b3. Those are the three measure numbers for those three column matrices. Next, the inertia matrix in two different axis systems if you want. So you're looking at already you have in a B1 system, you want to get in a B2 system, then essentially it is this. So in other words, it's a kind of generalizing what we have on the top. We were talking of a particular principal diagonal element, maybe I11 or maybe I22 or maybe I33, one at a time we were talking. Here we are talking of either I12 or I21 or I31, I23, etc. We are talking one at a time. But if you want to get all of them, the entire matrix at a time, you can use this matrix equation in order to get to that. So instead of column matrices that you had there, you have all square matrices that you have over here, where you're having the transformation matrix itself coming into picture, what we call as the direction cosine matrix, DCM, or the rotation matrix. That particular transformation matrix is over here, and this T is different from this. This is a transpose of that T that you're looking at, because we know that transpose gives you the inverse. And therefore, you have in a B1 system, if you already know I, you can get it in a B2 system, big B that we are talking about. So remember that in this you have a set of unit vectors, in that you have a set of unit vectors. So going from one to the other, you can essentially use this particular thing to manipulate. So this is where it's very interesting. So when you're looking at from a tensor point of view, you see that this is a second order tensor, and therefore you have two multiplications by t. If it was a first order tensor, namely a vector, which we saw examples of in the morning session, only one multiplication by t was sufficient to get to a vector from a B1 system to a B2 system. On the other hand, if you had a zeroth order tensor, which is a scalar, you don't need any multiplication at all. In other words, t power 0, which is identity. Okay, so essentially you have it the same in all, whether it's the B1 system or B2 system, the scalar remains the same. So it doesn't change from one system to the other. A vector changes by one level. A dyadic like I changes by two levels, because you have a quadratic multiplication, one before and one post. Okay, the principal moments of inertia and the principal axis. So now remember that we are talking a general case where the I matrix was fully populated, but there is a special case. You can find a particular direction for any given point C. In this case, the center of mass is what we are looking at, but it could be any other point for all you know. But we could choose for a particular point, a particular set of axes that we can always find, where the inertia matrix becomes a diagonal matrix. In other words, only the principal diagonal elements are in general non-zero. The others are all zero, the off-diagonal terms. So that's a simple case that you have. And of course, in the case where you have a plane of symmetry, this becomes very easy to see that one of those will be associated with those planes of symmetry. If you have two planes of symmetry, it becomes even simpler, and you already know that anyway it is zero in that particular case. So you can get about the planes of symmetry, you can define those principal axes. Now, principal axis, is something that a term that you would have probably found in elsewhere as well. So mathematically, it is exactly same quantity that we are dealing with, but the specific matrix that we are choosing to apply that principal axis thing is the inertia matrix, and therefore can we choose the axis with zero products of inertia even without planes of symmetry. Already we know when there are planes of symmetry, certain off diagonal terms will go to zero, you will have a simplicity. But in fact, when you have two planes of symmetry, we saw that it will always be a diagonal matrix, and therefore you already have a principal directions. But what happens if there is no plane of symmetry that you can identify? Even in such a case, you can always find a set of axes about which this particular thing happens. Once you do that, it will become very easy for you to utilize that in order to do a lot of derivations, because you have a diagonal matrix. Things become much simpler to all your equations become fairly simple. A lot of terms involving the products of inertia will drop off. So yes, how do we define this? This is essentially like an eigenvalue problem that you have. You're essentially multiplying I with that particular direction n as a column matrix. Then you get IP n over there, where IP is a scalar quantity that you are talking about, the particular value of IP that you are having over here. So that is essentially what you're looking at over there. So when multiplied by any orthogonal unit vector, this above equation will give you zero products of inertia, which is what you're seeing in the off diagonal terms over here, right? So the eigenvalue problem with respect to three eigenvectors, and those three eigenvectors, because it's a 3 by 3 matrix, in general it can have three eigenvectors. Some of them can be equal to each other, some of them could be zero, some of them could be complex, whatever, in a general 3 by 3 matrix. But in the case of the inertia matrix, you will end up with these three real values, IP1, IP2 and IP3, and depending on symmetry, some of them might be equal to the other. So principal moments of inertia about three orthogonal axes, and those corresponding directions about which these three are determined are called as the principal directions, n1, n2 and n3. So once again, all of these are very, very similar to any typical eigenvalue problems that you might have encountered in other fields, just that we are applying it to a particular matrix, and therefore it's getting tailored, and some of the terminology is associated with the inertia matrix. So use three principal axes as the rigid body axis, then you will end up with, of course, the moment of inertia about the center of mass being the simple diagonal matrix that we have already discussed at the beginning of the slide. Okay. Now Euler's Euler's dynamical equations about the principal axis. So now that we have introduced the principal axis, obviously that's the simplest case that you can have, because all the product of inertia terms vanish, they are off diagonal terms, and therefore you're left with only the diagonal terms. In that case, the relation between I and omega becomes the simplest that you can have for the three-dimensional body. So essentially you're looking at the x component, y component and z component of the moments which are external, the resultant moments that are there. Their measure numbers, of course, about the center of mass are related to your omegas and their omega dots by these equations. So once again, you have those omega squared terms, which are essentially centripetal terms, and you have the usual thing, which is like force is equal to mass into acceleration. Here you have the moment is equal to the moment of inertia, mass moment of inertia, times the angular acceleration. So that's the only difference. So in the translation, you just had this term alone, but now because you have rotation, you have these additional terms as well, which involve don't involve omega dots, but involve omegas, but as products of each other. So omega dot, see, omega already had a radian per second, and because of the dot you get a radian per second squared, but here you have omega squared, so you already have again a 1 by second squared kind of a different thing that you really need to multiply with I in order to get the dimensions of your moment, which is force times distance, which is essentially Newton meter. So this is the equation in the expanded form that we had, that is mxc, myc and mzc, when you had generic axis, because then you had a fully populated inertia matrix. In other words, you had non-zero products of inertia, right? Of course, it was a symmetric matrix, so you had only 6 independent terms, but in general it could be a fully populated thing. Then you had two terms. One is the acceleration, angular acceleration term. The other is the centripetal acceleration. All that you have done in that general equation is to set your off-diagonal terms to 0 in both these matrices, which is the same matrix, of course. So once the off-diagonal terms, namely the products of inertia, are all zeros, this is the simple set of equations that you end up with. Instead of a matrix equation, we are just writing it as a 3 scalar equations, because it's a 3 by 3 matrix that is involved over there. Okay, so just a few additional forms of the Euler dynamical equations, and then we will conclude the course as far as the lectures are concerned. Okay, see the Euler differential dynamical equations about inertially fixed point, because these are simple cases, remember, which will make things even more simpler than some of the things that we have looked at. Already we have looked at a simple case, which is the center of mass. So already it had its own simplicity. Now we are looking at another example of a simple case, which is an inertially fixed point, which we typically refer to as O, let's say the origin of the inertially fixed frame. So without loss of generality, it need not be the origin, it could be any point, any other point in the same inertial frame of reference, because you know that most equations that we have in dynamics are immune to the translation of the inertial frame of reference without rotation, and therefore whether it is O or some other point really doesn't matter as long as it is fixed in I. So we are looking at that such an inertially fixed point, and essentially this is the kind of equation that we would have. Looks very similar to the equation that we had earlier about C, only thing everything wherever we had superscript C, we have put a superscript O over here. Okay, so in other words it's equivalent, and this is understandable because remember that in going from saying that forces are equal to time rate of change of translational momentum to moments are equal to the time rate of change of angular momentum, we said that is possible only for two kinds of points. One is the center of mass, the other is for the inertially fixed point. So already we are done with Euler's dynamical equations for the center of mass. We want to do it for the inertially fixed point over here. Okay, so remember that for such a point, inertially fixed point like O, we had the sum of the external moments is equal to the time rate of change of the angular momentum about the same point O, and therefore that can be written as instead of taking the derivative with respect to I take the derivative with respect to the body fixed frame B, but then I have to add a term which is where this particular term comes, and that's the source of what you have over here, right? So omega B about I, that is the angular velocity of B with respect to I, crossed with the angular momentum about the point O. So we use the parallel axis theorem as needed, and therefore we got that. Now use of intermediary frames of reference in axisymmetric problems. So some of your problems we already talked about a single plane of symmetry, two planes of symmetry. Those are planes. Now there are problems which are bodies of revolution. So then you have an axisymmetric problem, and there also certain simplicity is possible, and which we can take advantage of instead of going to the generic equations, which is what we will look at over here. So use of intermediary frames of reference in axisymmetric problems. For axisymmetric problems, you can consider an intermediary frame of reference which we will call as G. Already we have an A and a B frame of reference. B is body fixed, A is fixed to the or A or I rather here. I is the inertial frame. So then you have between I and B, you are introducing this frame G that you have, in which the moment of inertia is the same as in the rigid body for a frame of reference which is B, right? So now the key in introducing this intermediate frame of reference is that the rigid body rotates only about the axisymmetric axis. So in other words, in general a body, even though it is axisymmetric, can be rotating about some other axis, any arbitrary axis. But suppose you have the rotation also taking place about the axis about which there is an axisymmetry for the body, then the particular simplification is there. So we can write the Euler's dynamical equations in either your B frame or your G frame of reference, or in fact any arbitrary frame of reference, but this is what is useful for this particular derivation. So you have your moments which are coming, which is taken about the center of mass for the expressed in the B system. That is, this column matrix has the first, second and third term along a small b1 hat, b2 hat and b3 hat. When you have that, then you see that using the generic equation that we have already developed, it is nothing but the inertia matrix for the same body about the same point times the angular accelerations, which is nothing but the time rate of change of the angular velocity. And then you have, that is not all, you have an angular velocity crossed with that particular quantity whose time rate you are interested in, which is what you see in this last term that you see over here. Okay, now if you assume that your IC in the G system and B system is the same, because remember we are choosing in such a way that the axisymmetry axis and the axis of rotation are one and the same. So therefore your about the G as well as B frames of reference IC remains the same because it's the same axis that you're dealing with, and that's a constant because of the axisymmetry that you have, and therefore you see that the Euler's dynamical equations in special intermediary frame of reference turns out to be this. So in other words, what is done over here is the B's are replaced by G's that you see over here, and that will be sometimes very useful because we can take advantage of the axisymmetries, and your I matrix will be much more simpler in writing about the axis of symmetry rather than any arbitrary direction. Okay, so the derivation of this is similar to the equation in the rigid body frame of reference, except for the differentiating the angular momentum in the intermediary frame of reference G that we have introduced. So in which case we invoke the same exact relationship. All that we are doing is to change B to G, okay, the intermediary frame of reference that we had. So once again, it's the external moments equal to the time rate of the angular momentum in the inertial frame, which is valid for the center of mass, and therefore it is given for any other frame, in particular the frame G, which is the intermediary frame we have introduced, such that the axis of rotation and the angular velocity vector are parallel to each other. Then we have this term that you have to add, which is omega G I cross HC. Okay. Then the intermediary frame of reference and a fixed point. So some of these things, remember that like the angular velocity, we could utilize it not only to describe the rotational motion, but also to calculate certain things. Same thing can be done over here, the intermediary frame of reference and a fixed point. So we can write the Euler dynamical equations for the rigid body about an inertially fixed point O in terms of the measure numbers in a special intermediary frame of reference. And it's special because the moment of inertia is unchanged in G, because that's both the axis of rotation and the direction of your angular velocity. So therefore we have this simplicity. So with this, I think we have completed the course. For the previous batch, I also gave a review of whatever we have done in the entire course. There's a recording of that, so I don't want to go through the whole thing once again. So for those of you who are interested, you can look at my last lecture from the previous season. Then you will see the entire review of the dynamics, whatever we have done in the course. So thank you very much for your patient listening. I had to go a little fast today so that we could complete by 4. But if you have any questions, I would be happy to answer now or later also. And Wednesday, of course, we'll be presenting 2 homeworks along with a few remaining problems from one of the last homeworks. Thank you. Thank you so much. I appreciate it. Thank you. Thank you. Thank you. Hope you enjoyed at least as much as, or maybe at least a part of what I did, because I thoroughly enjoyed teaching this class. And the interactions that we have had, it's been quite interesting. Thank you. Thank you. Thank you.